Greeting. Welcome to the podcast on random variables. In this podcast, we're going to go over what a random variable is and work with it a bit and find out what some of the properties of them are. So let's start off with the definition. A random variable is an uncertain numerical quantity whose value depends on the outcome of a random experiment. We can think of a random variable as a rule that assigns one and only one numerical value to each point of the sample space of a random experiment. Well, got some words we're going to have to take care of in there, okay? There's a whole bunch of stuff going on here, okay? So first of all, what do we mean by a random variable? It's an uncertain numerical quantity whose value depends on the outcome of a random experiment. So what we're talking about here is a random variable is a number. It's a numerical quantity, okay? And that numerical quantity is based upon the outcome of some random experiment or some event that occurred out of a set of things that are possible, okay? A good way of thinking of a random variable is a rule that assigns one and only one numerical value to each point of the sample space of a random experiment. So we're going to have to take a few minutes to define what this word sample space means. Sample space is very simply all of the possible events that can occur in a given random experiment. Okay? An example probably would be a good idea to help us drive this home. So let's take a look at one. How about if we toss a fair coin 3 times? So if we toss a fair coin 3 times, there are going to be 8 possible individual outcomes in this sample space. Since the coin is assumed to be fair, the 8 outcomes can be assumed to be equally likely. That is, each is assigned to an individual outcome of 1/8, or probability of that outcome. So let's talk about these tools that I've got set up here to help us kind of create the sample space. Notice that what we have here is what's called a tree diagram. And this is the first toss. And one of two things can happen in the first toss. We either got a heads or we got a tails. So let's assume that in the first toss we got a heads. So that would mean we're here. So now we move down to either heads or tails again. So in our second toss we have another choice of either getting a heads or a tails. So let's say in the second toss we got a tails. And then we toss the coin a third time. So now notice from where I'm standing right now, again I have a choice of getting either heads or getting tails. So let's say in the third toss I got a heads. So now that corresponding event, which is one of the possible events that can happen in my sample space, would correspond to this one right here, which is heads, tails, heads. And notice that if you walked along every branch of this tree diagram, you'd end up with all of the possible events that can occur in the sample space, okay? Now, what we also notice here is that since it's a fair coin, is that each one of these events, the heads or the tails, each can occur with the same chance, the same probability of being exactly 1/2. That is, the probability that in any one flip that I get a heads, if it's a fair coin, should be 1/2, right? So what is the probability of getting heads, heads, and heads? In other words, I flip the coin 3 times and I get heads 3 of those times. What's the probability of that happening? Well, it turns out that one way of looking at that or calculating that is that that's 1/2 times 1/2 times 1/2. So we do that calculation and we get 1/8, all right? Now that's the mathematical way of looking at it. It turns out that if each of those events were equal probable, then you don't have to necessarily do this calculation. It would change if those probabilities were different from each branch. Because why? Well, here let's take a look at what they're talking about here. There are 8 outcomes, 1, 2, 3, 4, 5, 6, 7, 8, and each of these are equally probable, so they all have a probability of occurring of 1/8. Okay. All right. Let's go back to some of our language here for a minute, so you make sure we understand what was going on with the English back here. Okay. So the sample space is all of the possible things that can occur in our random event or random experiment. So in this random experiment, everything that could possibly happen is a heads, 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 tails, heads, tails, heads, etc. Okay? The random variable, what that does is it assigns a numerical quantity or value to each of those outcomes in the sample space. Okay? So if I was to define my random variable here, let's go ahead and do that. And let's say that our random variable is going to be x, and x is going to be equal to the number of heads. So if that's my random variable, in other words, that's my, back up one more time here so you can read it, that's my uncertain numerical quantity whose value depends on the outcome of a random experiment, then notice what the random variable is going to take on as I go down this list in the sample space. The value of the random variable would be assigned to, or would assign to this particular event would be a 3, because there are 3 heads. The value of the random variable would assign to this would be a 2, because there are 2 heads. Here it would assign a 2 again. Here it would assign a 1. Here it would assign a 2. Here it would assign a 1, and then it would assign a 0. Okay? So if we take a look at what we've got here, we see that the possible values that the random variable can take on are 0, 1, 2, and 3. Okay? So one way of labeling that or setting that is in a is a probability distribution of the random variable. In other words, what I can do is I can list here all the possible values that the random variable can take on, 0, 1, 2, and 3. And then in the second row here is I can list the probability of seeing those particular values of the random variable. Okay? So let's come back here again. So from my sample space, I notice that there's only one way that I can get a 3, and there's only one way I can get a 0. There are 3 ways I can get a 1, and there are 3 ways I can get a 2. So what that means back over here in my table is that the probability of seeing a 0 for the random variable, well, that's going to occur 1/8 of the time. Probability of seeing a 1, I take a look at it again, see there's 1/8, 2/8, 3/8. Okay, so there's 3/8 for that. Let's go take a look at the 2. See, there's 1/8, 2/8, 3/8 again for the 2. And for the 3, there's only one way to get that, 1/8. Okay? So what we've just created is a probability distribution for the random variable that counts the number of heads in the flipping of a fair coin 3 times. Okay? Let's go back and make sure we got it. We'll go all the way back to the first slide here again. Okay? So the random variable is a uncertain numerical quantity whose value depends on the outcome of a random experiment. In our example right now, the random experiment is flip a coin 3 times. Okay? We can think about a random variable as a rule that assigns one and only one numerical value to each point of the sample space for a random experiment. Okay? So a random experiment, flip the coin 3 times. Our random variable counts the number of heads. So this particular event right here, I'm going to change color here for you. So just to start off with this one, so this particular color or particular event, heads, the random variable, since it's counting number of heads, would assign that a 3. Okay? This particular event right here, which is heads, tails, since it's counting the number of heads, the random variable would assign it a 1. Okay? Hopefully you're getting all that. Alright, so let's move on a little bit here. Got to fill in some gaps here with some of the rules about probabilities. If an event, to any event A, we assign a number, P of A, called the probability of event A. So for example, back here, if I had said, what is the probability of getting a 2? Probability of getting a 2 is 3/8. I can read that right off of my table. Okay? In other words, I just grab what the value is. In this particular case, it's a 2 that I'm looking at. Look at that in this part of the table and go down to it, and I've assigned to it a probability of 3/8. Okay? Assign a probability to each individual outcome, each being a number between 0 and 1, such the sum of the individual probabilities is equal to 1. Well, what do we mean there? Well, in the wrong direction here, sorry about that. What we mean is that if I take a look at all of the P of X's here, I'll notice that the sum of these P of X's has to be equal to 1. Okay? Another thing that we notice is that if you take a look at any one of these individual probabilities, that any individual probability in this table is going to be less than or equal to 1, but greater than or equal to 0. All probabilities reside between 0 and 1. You'll never have a probability bigger than 1 nor less than 0. Keep that in mind. That's important. Okay? Alright. Probability of any event is the sum of the probabilities of the outcomes that make up that event. We'll talk more about that one in just a second. But what we're saying is if my event is I want to flip heads, say 2 or 3 times, and that's what I'm looking for, then it would be the sum of the outcomes that make up that event. If the outcomes of the sample space are equally likely to occur, the probability of event A is simply the proportion proportion of outcomes in the sample space that make up the event A. And that's what we just did in our previous example here, because they were all equally likely. And that's nice when that happens. It's not always going to happen, so don't get used to it, but it does happen fairly often enough, okay? All right. Let's go talk about the different types of random variables that exist out there. Now, if you recall from our earlier discussions about continuous and discrete variables, we're going to just extend that idea now to random variables, all right? So we'll start off with a discrete random variable. And let's take a look at some examples here. A discrete random variable can assume at most a finite or infinite but countable number of distinct values. Key thing to keep in mind when you're trying to decide whether it's discrete or continuous, you're counting something. If it's counting something, it's discrete. If you're counting it, it's discrete. If you're measuring it, it's continuous, okay? We'll bring that up over and over as we go through this. So a couple of examples, kind of graphic ones to make you think about it. Number of eggs a chicken lays in a day. And if you think about eggs coming out of a chicken, I know they come out countable. They don't get 1.5 eggs out of any chickens that I know of, at least. Number of bombs dropped on a city, number of children in a family, all of those, number of things. As soon as you see this word, the words number of, that's a very large hint that we're talking about a discrete random variable because it's something you're going to count. Okay, contrast that to a continuous random variable. A continuous random variable can assume any value in an interval or collection of intervals. It always has an infinite number of possible values. So, for example, gallons of milk from a cow over its life. Now, I've had many people ask me, okay, well, gallons of milk, you're counting. You can count the number of gallons of milk. Well, that's the unit we have chosen to measure in. The underlying phenomena is continuous. We have to pick a unit to measure at, and it could be tenths of gallons, hundreds of gallons, millions of gallons. We get to decide the level of accuracy as the researcher, but nonetheless, the underlying phenomena is continuous. So when you have a continuous phenomena, it's something you're measuring. That's a real key to help you out there, okay? Number of hours that CNN broadcasted the Iraq War without interruption. Number of hours of battery will run in a flashlight, okay? You got to be careful here because that number of is showing up here again, but it's the thing that's going to key you off here is hours. As soon as you see anything to do with time, you know it's going to be continuous, okay? So be careful what I said about the number of and make sure that you quantify that also with whether or not it's an underlying continuous phenomena, all right? Okay, so let's go take a look at some examples here of random variables. Let's say x is the difference between the number of heads and the number of tails obtained when a fair coin is tossed 3 times. So we want to give the values that the random variable can take on, and we're going to decide whether or not it is continuous or discrete, okay? So let's see. It's the difference between the number of heads and number of tails obtained when a fair coin is tossed 3 times. Well, let's go back to our example here that we did earlier. I'm going to slide back a few slides here. Okay, so now what the random variable isn't counting the number of heads, it's counting the difference between the heads and the tails, okay? So, back up one more time to the definition. Just put these slides next to each other so I don't have to go so far. It's the difference between number of heads and number of tails. So it's the difference between heads and tails. We're subtracting the number of heads. From that, we're subtracting the number of tails, okay? So, what we see here, just a second here, I'm going to clean this up to make it a little easier to see what we're doing. What we see in this case with this random variable, there we go, get it all prettied up here for you, is that now we have x is equal to number of heads, let's make that a capital H, subtract number of tails, okay? Alright, so what are the values that the random variable can take on? Well, number of heads minus number of tails in the first case, in our first event right here, well, that's still going to be 3, isn't it, right? Because, you know, you take no tails away from 3 heads, and there you go, right? What's the difference here? We got heads, there are 2 heads, minus number of tails, that's going to be what? That's a 1, isn't it, right? And again, you've got 2 heads minus number of tails, so that's going to be a 1. And now we've got heads minus 2 tails, that's going to be a -1, isn't it, right? And then we've got a 1 again, because we've got 2 heads subtract 1 tail. And you got one head minus two tails, that's going to be a negative 1. And then we've got two tails subtracted again from a head, that again gives us another negative 1, right? And then we have three tails, which is going to give us a negative 3. So the values that the random variable can take on look like they're going to be negative 3, negative 1, 1, and 3. Okay? Hopefully that makes sense what I was just doing there. But one of the big things I really need you to see here more than anything else is that it's a discrete random variable. So it can only take on negative 3, negative 1, 1, and 3. Those are the possible values. Okay? What if y is the product of the pips for rolling two fair die? How would you do that one? I'm not going to complete this whole thing for you. I'll just give you a hint on it, okay? But what you have to do is list out all possible values that two fair die can take on. So we'll do 1 by 1, meaning that I rolled snake eyes. 1 by 2 means I rolled a 1 with the first die, 2 with the second one. 1 by 3, and then all the way up to 1 by 6. And similarly, I go down this way. It would be 2 by 1, and then 2 by 2, etc. Okay? Now, once you've completed this table in both directions, you have to go through and find the products of each of the pips. Well, 1 times 1, that would be one of the values x could take on would be 1. Another value could take on would be 2, 3, etc. But remember, we're taking the products here, aren't we? Right? Okay, all the way down to, notice down in this corner is going to be 6 by 6. So all the way up to 36 is one of the possible outcomes that can be in there, all right? I'll let you fill in the gaps. We'll talk some more about this table in an LDI in just a few minutes, okay? But the main thing to see is, again, that this is a discrete random variable, all right? Okay, let's take a look at R. R is the time in minutes that this class lasts. Oh, I know, that one seems like it could be infinite, isn't it? Well, the thing is the main thing you need to notice here is that it's T for time, okay? So it's going to be an interval. So let's assume that it's a standard lecture and that you're not doing this as an online course. So in a standard lecture, it's usually anywhere from 0 to 120 minutes for most statistics class, okay? And notice I'm using interval notation this time because this is a continuous random variable. So in order to be able to list all possible values, I have to use interval notation. Now, alternately, I could use set builder notation. It's the set of r's such that 0 is less than or equal to r, which is less than or equal to 120 minutes. Okay? Alrighty then. I believe that's everything that we've got to talk about. No, I'm sorry, we don't. I got one last slide. I almost lost track here. A discrete random variable can assume at most a finite or infinite but countable number of, big things, countable number of them. A continuous random variable can assume any value in an interval or collection of intervals, okay? So main thing is any value. So if you can take on any value in the interval, you know you're continuous. If it's countable, you know you're discrete. Okay, now we're done. Okay, folks, I'll see you all back here for the next LDI.